So now we're in section 4.3. One of the most important things to remember is that 4.1, 4.2, 4.3 come together as a single idea, linear regression, where you have two sets of quantitative data that can be viewed as ordered pairs. You're trying to find linear patterns between those two quantitative variables. The first thing you do is set up a scatter plot. That's what we looked at in 4.1. Once you've determined that your scatter plot reveals a fairly nice linear pattern, a fairly strong linear pattern, then what you do is you proceed into 4.2 and you come up with the equation of the best fit line or the regression equation line, synonymous phrasings. And now we're in 4.3, finishing off this idea of linear regression with something called coefficient of determination. Now look at the screen in the red box in the lower left. One of the most important things that you can do right now before we start is understand that there's two ideas. In 4.1, we introduced the idea of the correlation coefficient, little r, which measured the strength of the linear relationship between the two quantitative variables. There's something related but slightly different called the coefficient of determination. It's important that you keep these two phrases, these two symbols separate. Little r, correlation coefficient, capital R squared is called the coefficient of determination. Now, a brief clarification. Do you see where it says capital R squared? That's really, mathematically speaking, just little r squared. The coefficient of determination is just the square of the correlation coefficient. So look what my cursor is. Little r squared is really capital R squared. I don't like that. There's nothing I can do about it, however. What you have to do is just keep it straight. They both measure the strength of the linear relationship, but they do it in a different way. Little r gives us a positive and negative value, which tells us whether we have a positive or negative association, aside from giving us a number that measures the strength of the linear relationship. Capital R squared, capital R squared gives us something else. It doesn't give us the plus or minus. What it gives us is the percent of change in the response variable that can be explained by changes in the predictor variable or the explanatory variable. Again, the importance of capital R squared is that it gives us the percent change in the response variable, the y variable, that can be explained by our model and changes in the explanatory variable. We'll elaborate upon that in the section, but slow down here and try to think about what I'm saying. Look at this right here. We have a scatter plot. We have this xy coordinate system. The x-axis and the explanatory variable is the number of hours studied. Number of hours studied. And the response variable is the points achieved on the final exam. The mean score for the final exam was 62, the black line that you're seeing right here indicated with the cursor. I'm going to ask a question. It's going to sound a little bit silly, but why don't all the students score all the same grade? Why doesn't everyone get a 62 if that's the mean score? There are a lot of reasons. Number of hours studied, preparation for the class, stress levels, whether they're working a part-time job or not. If you think about it, there are many, many different variables that will influence test scores. We're trying to primarily explain the change in the test scores in terms of number of hours studied. So we create this model. This is our best fit line that best fits the data. And it does indicate that we have this general linear pattern with a positive trend, meaning as the number of hours increase of study, the grades seem to trend up. All right. But why did John, right here, why did John score so much higher than predicted? Why did Anne score less than predicted? Because there's other variables at play other than the number of hours of study. The coefficient of determination, capital R squared, measures how much of the change in the y variable, the response variable, in this particular case, the grades, how much of a change in the grades can be explained solely through hours studied. Okay, we'll talk about that more later in detail, but that's the main idea. Why doesn't everyone score the mean score? Well, some factors are influencing people's grades. There's probably many, many factors that influence people's grades, but we're trying to narrow it down and explain the change in terms of number of hours studied. But obviously that's not sufficient. If hours of study explained everything, we would have little r equaling 1, and all the dots would be on the line. There are other factors involved. The point of this section is to talk about this coefficient of determination, capital R squared, and that will give us, that numerical value will give us what percent of the change in the response variable can be explained by changes in our explanatory variable. You have something called total variation and explained variation, right? Okay, because capital R squared is squared, it has to be between 0 and 1. If R squared equals 1, that means that the model explains 100% of the variation in the response variable. If R squared equals 0, then the line has no explanatory value. So let's go back to our drilling example. Here's our scatter plot. You know, we see a fairly nice linear pattern. We create the best fit line. Here's the equation of it. Y hat equals 0.0116x plus 5.5273. Does our model explain everything about the change in time? No. We're primarily trying to explain the change in time it takes to drill 5 more feet through how deep we are. Okay. But why is this dot above the line? Why is that dot below the line? Well, there are other factors at play, right? The hardness of the soil, whether you're drilling through rocks or sand, etc. But we're trying to primarily explain the change in time through change in depth. How much does this model explain? That's the coefficient of determination. So let's get back to some basic ideas. First, we compute the mean drilling time at 6.99. Okay, look at it on the graph. Here's the mean right here, 6.99. Why don't all the drilling times equal the mean of y bar equals 6.986? Because there's factors, or explanatory factors, influencing the drill time. We're trying to explain it primarily in terms of depth. And so the distance between the mean, the red line right here, and the model line, the best fit line, that's the difference explained by our model in terms of depth. Why did this dot end up higher than the line? We don't know. That's called unexplained. Okay, explained by the model, unexplained. Now, if the dots are below the line, it'll work the same way, and the definition holds true. It's just easier to talk about it visually when you put the dot above the line. But again, why don't all the drill times equal just the average drill time? All right. Well, we're trying to explain it in terms of depth. The model explains this much of a change away from the mean, and the rest of it's unexplained. Now, suppose you were asked to predict the time to drill an additional 5 feet, but you didn't know how deep you were. You had no information whatsoever. Your best guess would just be the mean time, right? If you have no idea. But we're trying to explain this in terms of depth. And so if they say, look, use your model and make a prediction based on the depth being 160 feet, you just plug 160 into your model, okay? And your guess increased to 7.39 because that's what the model predicts, you know, by putting that in there. Again, you have this idea of total deviation away from the mean, total deviation away from the mean, which is y minus y bar. Look at this. Here's y bar. That entire distance is the total deviation. Then you have something called explained deviation. That's the distance between y bar and y hat. Y bar is the mean right here, y bar. And remember, all y values on the line are designated by y hats. Then you have unexplained deviation, but remember that's the residual as well. So this unexplained deviation is the discrepancy between our model and the reality of the observed values. Okay, and so this unexplained deviation just takes us right back to the definition of what a residual is. This right here is y bar. This right here is y. The total deviation is the distance between the observed value and the mean. Okay, the model explains this much of a change, and so that's going to be explained difference. Okay, this much is unexplained by our model. There are other factors involved. Total deviation is the distance between the mean and the observed data value. Explained deviation is the distance between the mean and the line. And the unexplained deviation is the residual. It's the discrepancy between our model and the observed score, y minus y hat. The same picture, Total deviation, the distance between y bar and the data value. Explained by the model, the distance between y bar and the line. Unexplained, the distance between the line and the data value. Again, this will work even if the dot's way down here where the cursor is right here. The definitions hold true. But what we have is total deviation equals unexplained plus explained. So this is going to make this much easier. For the most part, I just need you to know what capital R squared is. It's the coefficient of determination. How do you find that? Well, you compute little r. Look here, little r is 0.773. You square that. That's capital R squared. In this particular case, it's 0.5975, which means our model explains 59%, 59.75% of the change in time is determined by the depth. So how much does our model explain? 59.75%. What does that mean? What that means is, as we increase the depth, the times increase, but it's not a perfect fit. We have discrepancies. How much does the model explain about the change in drilling times in terms of depth? Capital R squared, that 59.75%. So here, see how the dots are almost all on the line. We take R and square it, and we get 99.99%. This is our capital R squared. This is what it would look like if you had 94.7%, and this is what it would look like if you only had 9.4%.